It's a great honor for me to introduce the second keynote speaker, Professor Peter Glynn. Peter is very well known as one of the true luminaries in our field. And quite frankly, it's difficult to even start describing his extraordinary scientific contributions and leadership roles in the community. So again, I'll just briefly mention some of the highlights. Peter is the Thomas Ford Professor in the Department of Management Science and Engineering at Stanford University, where he also holds a courtesy appointment in the Department of Electrical Engineering. He has served in numerous leadership positions, both at Stanford and in the research community, in particular in the Informs Applied Probability Society. And he has played major editorial roles, in particular as the founding editor-in-chief of Stochastic Systems, editor-in-chief of the Journal of Applied Probability and Advances in Applied Probability, and as editor of Mathematics of Operations Research, all flagship journals in our field. Peter is the recipient of many notable awards and distinctions, in particular the Outstanding Publication Awards of Informs Simulation Society, no less than 3 times, even the Best Publication Award from the Informs Applied Probability Society, and the John von Neumann Theory Prize from Informs. He has also given prestigious lectures, including the Markov Lecture in 2014 and the Informs Philip McCord Morse Lecture in 2020. Peter has been a wonderful mentor and source of inspiration for many young researchers, and these are not just his own former students who now hold positions at top academic institutions, but I would say that almost all the leading young or not so young researchers in our field have crossed paths with him one way or the other and greatly benefited from his expertise and guidance. Peter has made groundbreaking contributions in the area of simulation, computational probability, queuing theory, and statistical inference for stochastic processes. And in his talk today, entitled Statistics, Stochastics, and Queuing, many of these research lines will come together. Peter, the floor is yours. Please go ahead.
Well, thank you so much, Sam. That was a lovely introduction. And I'd like to thank the organizers for inviting me to give this talk today. It's a great privilege to have this opportunity. It brings together a bunch of different threads that I've been working on over the last years. And as the title indicates, I'm going to be touching on statistics. I'm going to be relating that to the stochastics theory that we have all contributed to over the years. And of course, doing this within the context of queues. So when one builds statistical models, one typically, I think, at least in our world, we're building statistical models for purposes of making a better decision. So there's a purpose to why we build a statistical model. And I'll come back to that at various times later in this talk. That'll be a theme that will underlie a lot of the things that we'll be doing over the course of the next roughly hour. When you build statistical models, we know that a statistical model is not going to faithfully represent every single feature of the underlying data set. We have to pick and choose which features are important. And it's in that sense that theory can often be useful in telling us what features to reproduce in a statistical model. Of course, the most obvious starting point for building models is the Poisson process. I'm going to be focusing today, by the way, primarily on modeling of arrival processes. So in contrast to Moore gave a wonderful talk, by the way, Moore focused on the service times. I'm going to be focusing on the arrival process. And the most fundamental of all arrival processes is, of course, the Poisson process. So I'll just review some of what the theory says about why we should expect Poisson processes to arise. And then I'm going to talk about what the data says. And then I'm going to talk about a set of what I would view as being exploratory data analysis tools, primarily for application in the service operations context. So service operations environments that we're going to be thinking about will be things like, for example, call centers. So the timescales that come up in that context are much longer than the timescales that arise in the computer system setting that Moore talked about earlier this morning. And that will have an effect on the way we think about doing data analysis and model building. Then I'm going to talk about model building in the context of high intensity arrivals, some preliminary ideas on this, and some contrasts against low intensity arrivals. I'll mention that all of the work I'm going to be talking about today is in various ways joint with my former PhD student, Ziyu Zhang. So in terms of thinking about what happens when we have data available to build stochastic models, in particular queuing models, we start from the data, we do statistical analysis, we build the model, and then hopefully we make decisions. So it looks like it's a one-way street from data to statistical analysis to model decisions. But of course, building models successfully is also typically an iterative process, and we should think about it in that way. So more precisely, what we're going to be talking about today, and our goal in general is going to be tightening the link between statistical modeling of data and its use in decision-making, and in particular, in the type of operations management applications that I mentioned a moment ago. So in the world of computer systems, where the timescales are much shorter, you would have a different set of things that I think you would think about as being first order. So in the operations management environment, when you think about the use of statistical models, there might be, I think, two quite different settings in which a statistical model could be useful. One is in the context of planning problems, where the decision horizon is weeks or months or years into the future. And then what I might call operations problems. Operations problems are problems where you're effectively trying to make decisions in real time. The types of scheduling problems that Moore was talking about would be more of the operations type. So in this context, the objective involves a short-term decision that depends, that is contingent upon the current state. And of course, in the context of a planning problem, what the objective function might involve an expected value of, let's say, some stochastic process x of t. Whereas in the context of a operations problem, a real-time decision-making problem, there typically the decision will be contingent on the current state. So at some level, fundamentally, one's thinking about a conditional expectation. And building models that are accurate at the level of computing conditional expectations is a much more challenging problem than the problem of trying to compute something which replicates unconditional expected values. So I'm going to focus today on planning problems in which we're looking basically at unconditional expectations. Now, for planning problems, the decisions often involve answering what-if questions. So questions might be along the lines of what if we, for example, added more staffing to a call center, increased the number of people staffing the call center from, let's say, 100 to 120. Or we might just replace our software system with one that is capable of more sophisticated skill-based routing. We might then do simulations to understand what the potential impact on quality improvement would be in that setting. Or in the setting of airports, at least in the pre-pandemic era, we often were going through those checkpoints at airports. What would happen if you added another machine at that checkpoint? So all of these problems are problems that are what-if problems that arise in the context of planning. And again, the timescales that we're thinking about, the decision horizons, would typically be fairly long decision horizons. We're adding more staffing to a call center. It might be that it would take several weeks or several months even to do the hiring. And then given all of the frictional effects involved with adding people or potentially removing people from a call center, downsizing the call center, that problem would, whatever policy one would adopt would be something that would likely be in place for a fairly long period of time. So I think one interesting question, maybe this is something that we'll come back to in the discussion that follows my talk, is the question of why build statistical models at all? So in particular, if you have a lot of data, why can't we just use the empirical data directly? That's a question that I think probably many of us get and probably many of us have thought about. I'm just going to talk now a little bit about what some of the problems are in using empirical data directly without doing any modeling whatsoever. So one problem, of course, is that sometimes you may just not have enough data to be able to make reasonable distributions from which to run simulations or from which to construct stochastic models. Another problem might be that you don't have enough representative data. So you can see on this slide a time series of arrivals to a system in which the number of arrivals is gradually increasing over time. The first vertical red arrow is pointing to, let's say, current time. Then you see a second red arrow that's pointing to the time at which the decision is actually going to be deployed. And we can see, of course, that if there is some sort of background trend that's increasing the number of arrivals to the system, we obviously need to take that into account in terms of the decision that we're going to make, what we're going to actually deploy at that later time. And of course, the data that we've seen historically is not going to be fully representative of what we expect to see in the future. So just using the raw empirical data up to current time would underestimate the number of arrivals to the system at the future time at which the decision is going to be deployed. And then you get into a whole bunch of interesting questions about how you would potentially model the arrival process at that deployment time based on existing data. The most obvious thing to do, of course, would be you want to increase the arrival intensity by a certain percentage. And the most obvious way of doing that is by rescaling, for example, the inter-arrival times. Just run the arrival process as it's existed historically at a faster rate. That'll certainly increase the arrival intensity. But of course, what happens when you do that is that if the arrival process includes things like autocorrelation effects and various other things, these are things that, as we'll discuss later in this talk, actually are quite important in many of these operations problems. Then that autocorrelation structure is not going to be reflected correctly when you just speed up the process. In particular, the decorrelation time at which the arrival process will decorrelate will get shorter commensurately. That's probably not something that you'd like to see happen in the arrival model that you use in terms of making the decision at that deployment time. Of course, another thing that could happen is that you believe that it's likely that the customer mix that you're going to be seeing at deployment time could look somewhat different than the customer mix that you've seen historically. Again, there's no easy way to toggle those kinds of things just based on the empirical data itself directly. So this raises a bunch of questions then about how to address situations of this kind. And really, at least in my view, the only way that you can really deal with these issues in a principled way is to somehow model the data. So modeling is going to be important in terms of addressing issues of this kind. So the view that I'm going to take today is a view in which we have a system of some kind, a queuing system, and we are modeling the exogenous arrivals to that system. So we have in mind a arrival process that brings in arrivals from the outside world into the system. And you'll see in this view of the exogenous arrival process, there is no feedback from the system back into the arrival process itself. So this is often a pretty good assumption to make, but not always, of course. There are settings in which the system itself can impact what I'm calling the exogenous arrival process. And a good example of that, of course, is retrial queues, where if somebody is blocked, let's say doesn't get service, that individual may call them back again another hour or two later. And that creates a feedback between the system itself and the exogenous arrivals. So exogenous arrivals in the way that I'm going to be describing them today is an idealized framework. Nevertheless, it's an important and useful framework. So there are really two fundamentally different settings. One is the setting of high intensity arrivals, where the expected number of arrivals per service time is large. So again, oftentimes when we talk about high intensity arrival processes, we talk about this is an arrival process where the number of arrivals per unit time is large. I think that's not a good description of these systems, frankly, because of course, how we measure time can radically affect that arrival rate. So you really need to think about something that's more fundamental. And the more fundamental thing is what's the expected number of arrivals per service time? What you'll see, for example, in call centers is that the inter-arrival times are in the order of seconds, and the service times in that context are in the order of minutes. So the number of arrivals per service time is large in that context. That's what leads to a high intensity arrival process. So it's always good, I think, in thinking about stochastic models to try to frame the asymptotic regime of interest in terms of something that at some level is dimensionless. The dimensionless ratio in this context is expected number of arrivals per service time. And there are situations where the arrival process is of what I'll call low to moderate intensity arrivals. That would be things like emergency rooms and these TSA checkpoints. Okay, so the fundamental building block that I think many of us start with when we think about building arrival processes is the Poisson process. And there are many, many justifications that you can find within the literature for settings in which Poisson processes will naturally arise as good approximations. And probably the one that we most typically think about as being a good justification for the Poisson process is the superposition setting, where we imagine that the arrival process to the system of interest is really the superposition of arrivals from a large number of independent sources. Imagine that n is the number of independent sources, and we're going to let n go to infinity. And of course, in order that the arrival rate remain bounded, we're going to assume that the intensity per source is scaling at the rate 1 over n. Let's say intensity lambda divided by n. And then there's a large number of different limit theorems in the literature that say that that point process, n sub n, constructed from n independent sources when the number of sources n is large, regardless of what the structure of the individual source point processes is. In great generality, that superposition process will converge to a Poisson process. And that Poisson process will have intensity lambda. Now, one thing to maybe think about a little bit here is the Poisson process environment is quite different from the central limit environment that many of us are also familiar with. In that setting, of course, you begin summing random variables together. And the more that you sum the random variables together, the more Gaussian things look. And so that Gaussian assumption gets better and better the longer a time scale one looks at, because there are more and more things that you're typically summing together. In the Poisson process environment, you think about point processes. If you begin looking at shorter and shorter time scales, well, shorter and shorter time scales, eventually you're going to come down to intervals that have either just no arrivals in them or one arrival in them. And so in the context of point processes, you typically see the Poisson processes, that assumption gets better and better the shorter the time scale that you look at, not the longer the time scale you look at. And we'll see in a moment what that consequence has for the modeling and for the superposition principle that I just discussed. Let me also just mention that in high intensity settings, when the arrival rate lambda is large, of course, Poisson random variables satisfy the central limit theorem. They are effectively sums of IID Poisson increments. When you let the Poisson arrival intensity lambda go to infinity, you get a normal approximation in which the normal approximation, normal random variable has mean lambda and variance lambda. You just match the first two moments of the normal to the first two moments of the Poisson. So that's the square root staffing heuristic at some level that we see for call settings. So to handle non-stationary behavior, of course, that's going to be a very, very important factor in the context of operations management style problems. Again, this is not something that would arise in a computer systems environment typically, but in the OM setting, there are significant time of day effects, day of week effects, et cetera, that are present in many of these service systems. And that is a first order effect that needs to be built into the model. And we can do that quite easily within the Poisson paradigm by just allowing the arrival intensity lambda of t to vary as a function of time of day t. So in the first graph on this slide, you see that the lambda of t is varying in some non-constant way. And then the second graph on the slide is just the integrated intensity capital lambda of t. And it's worth recognizing that, in fact, you can see by the naked eye, lambda of t sort of looks like a probability density function. The capital lambda of t sort of looks like a cumulative distribution function. And in fact, that correspondence between intensities and densities and cumulative intensities and cumulative distribution functions is a very tight connection in the sense that of course, when we condition on the number of points in an interval, those points can be viewed as being an IID sample from a particular density, and that connects up intensity estimation to density estimation. So those two things are closely connected. All right. So superposition theorem says that we should see Poisson structure at time scales on the order of interrival types. When I say that, the superposition theorem is rigorously stated as a theorem on the involving weak convergence on the Skora-Hud space D0 infinity. And that theorem basically is a rigorous statement that we see Poisson structure at the time scale in the order of interrival times. Now, if you think about the call center environment is an environment where the service times, as I mentioned earlier, may be on the order of hundreds of interrival times. So from the standpoint of service times within that call center environment, we're looking at very long time scales involving hundreds of interrival times. Now we need to think a little bit about what does the superposition theorem look like at longer time scales. And one of the things that I don't think is so well appreciated with regard to superposition theorem is what I'll call the Poisson breakdown phenomenon, namely that rigorously speaking, one begins seeing non-Poisson effects emerging at the scale of square root of n arrivals, where n is the number of sources. So this Poisson breakdown result says, maybe not surprisingly, based on what I said earlier, that the Poisson approximation is an approximation which gets better and better at shorter and shorter timescales. It's not surprising that when you superimpose many independent sources together, that there would be some breakdown point at which that assumption begins to go to pieces. And this Poisson breakdown result that I just mentioned here, it's not too difficult to prove, is that in the superposition context, the Poisson breakdown begins occurring at this square root level. Now, here's another example of such a result. This is in the context of independent scattering. So independent scattering is one of the other settings in which one sees Poisson limit theorems. So independent scattering is take n points, throw them into an interval IID according to some distribution, and then the result asserts that the randomly scattered points do end up looking, roughly speaking, like a non-stationary Poisson process. Now, at what scale do you see that? You basically see it at the scales that are small relative to the size of the interval that you're looking at. So if you throw lots of points into an interval of length 1 hour, you're going to see the Poisson breakdown effect occurring if you look at intervals on the order of minutes. When you go down to intervals on the order of seconds, then you'll see things that look much more Poisson. So the point is that in lots of the limit theorems that we depend upon in the world of applied probability that motivate the use of Poisson processes, many of them, not all of them, but many of them exhibit this Poisson breakdown phenomenon. So we need to be aware of this, and we need to sort of acknowledge this in the way that we do statistical modeling. By the way, make a point here about the fact that the square root staffing idea that I mentioned a couple of slides ago is not a law of physics, so to speak. With the right modeling assumptions, even modeling assumptions that I think could be reasonable in some settings, you don't get square root fluctuations. You can get larger scale fluctuations than square root. So for example, if in an internet community, there's a cooperating sub-community within the n sources that all tend to let's say, access the web simultaneously based on some sort of rumor or based on some kind of common information that they receive. If that common sub-community tends to have a size that's larger than square root, you will see fluctuations of significantly larger magnitude than square root fluctuations in that context. So the main point here is that there are semi-realistic models where you don't get stochastic fluctuations of order square root. That means that within our world, square root staffing is not a law of physics. It's something that at the end of the day, you need to look at the data to see whether square root staffing is appropriate or not. At least that's my own personal view. Now, is there extra variability present in real arrival streams? In other words, we know for Poisson arrivals that the dispersion factor, the variance of n divided by the expected value. We know for Poisson random variables that ratio is always equal to 1. Over dispersion corresponds to the setting in which the dispersion ratio, the variance divided by the expected value, is potentially significantly bigger than 1. We all know at some level that many real world arrival processes exhibit this kind of over dispersion. So now I want to talk a little bit about a data set that Zhu and I have looked at. This is City of Oakland in California, Oakland City Service call center data. We have a call center running 24 hours a day, 7 days a week, over 4 years. So that's the time series that we have. And we looked at the random variable corresponding to total daily arrivals on each Monday of the week. So we did that in order to eliminate day of week effects and so forth. Now it turns out when you compute the amount of dispersion in that sample, it's very large, 28.1. Now, what does that mean from a modeling standpoint? What we would typically do then in this context is, wow, that's a big over dispersion. We're going to need to build some sort of model that reflects that, maybe using busyness factors. That's a concept that we'll discuss a bit later in this talk. And we're going to try to build an over dispersion that reflects this 28.1 ratio. Now that's going to get used down at the time scale of hours or days within, let's say, a simulation model or within a stochastic model that we built. So on the basis of this 4-year time series, we will be using that to build a model that is representative of the behavior of the system at the 1 hour or daily time scale. So now let's look at this data set a little bit more closely. So here's the first part of the data set. And here's the full data set over the 4 years. Now you can see that when you look at the full data set over the 4 years, you can see that there's actually a bit of a secular trend that's present in this data set. The number of arrivals is gradually increasing over the 4 years. And I think the amount of increase over the 4 years was something in the order of 30%. So about 7% per year. Now, you might think that's okay. The over-dispersion that I did is not going to be potentially impacted by that because I'm looking at things down at the order of hours or days. But in fact, the presence of a background secular trend actually has a very, very big impact on the sample over-dispersion ratio that one computes from the data. In particular, just the presence of the background trend is clearly significantly increasing the range of the data. The high values are on the right-hand side, the low values are on the left-hand side. And the fact that the range is as big as it is has something to do with the fact there's a background trend that is present. So I'm going to now discuss this in a little bit more theoretical detail. Let's look at a model for this. We have arrival counts, C1, C2, and so forth, corresponding to the number of arrivals on each successive Monday. We have a bunch of Poisson processes, n sub I. We have some kind of background intensity function, lambda. So imagine now that the interval of interest, the 4 years, corresponds to the interval 0, 1. And we have some kind of nice piecewise continuous deterministic function, which is describing the secular trend. We have a bunch of IID positive random variables that will increase the dispersion in some appropriate way, add some randomness into the model. They have mean equal to 1 and some c squared. And then the actual counts that we observe is given by ni of lambda I, where lambda I is now random. That's the extra randomness that we're building into the model in order to be able to create the over-dispersion. And lambda I is equal to gamma I times this slowly changing function of lambda. So again, think about lambda as being a nice continuous function. It doesn't change very much over each successive time step. Now, if you compute in this model environment, if you compute the sample variance divided by the sample mean from this count data, the key point is the limit theorem in the middle of the slide. M hat n converges in probability to m, and where what is m? M is equal to 1. That's the Poisson over dispersion or dispersion factor. Then there's a factor that depends on c squared. And then notice there's another big factor that is added onto this, which involves basically the fluctuations of the intensity over the interval 0, 1 away from the average value over the interval. Now you can see, of course, that when lambda is not a constant function, that second piece could potentially be very, very big. And that second piece is not coming from statistical variability, extra variability that's being reflected at the 1 hour or 1 day time scale. That's just stuff that's sitting there because you did not correct for the fact that there was a secular background trend. So this actually can be a very big effect. You can correct for this background secular trend by doing something that I'll call local averaging. So rather than using averages that are computed over the entire length of the time series, you do local averaging to compute a local estimate of the mean, and then you compute variances relative to that. When you correct in that way, then you get a new corrected empirical overdispersion that goes down to 7.0. So a massive decrease in the sample overdispersion factor. Now this issue is probably not an issue when you have a short time series of arrival data that you're looking at, but we all are greedy when it comes to data. The more data, the better. And the problem with the more data that you have is there's more likelihood that you have some sort of background secular trend that's sitting inside it. And if you don't make these kinds of corrections, you can see that it has a very big impact on some of the most fundamental statistics that we use within the world of stochastic modeling and queuing theory. So background secular trends can have a very big impact on measured overdispersion. Okay, so even the overdispersion that we did compute after correcting for the background secular trend, it's still 7. We'd still like to somehow deal with that additional variance that's present within the arrival process and model that in some appropriate way. And of course, the standard way of doing that is through a busyness factor, which just involves taking a deterministic non-stationary intensity lambda t and multiplying it by some random busyness factor gamma, where the gamma without loss of generality can be assumed to have mean 1. So when you do these kinds of models, and we assume, we look at the condition on the number of arrivals in some interval being equal to, let's say, k, then we know that the arrival times within the interval are distributed as an IID sample from a CDF given by a, that basically can be easily computed from the integrated intensity function lambda. Notice that this F function, even when we multiply by the busyness factor gamma, that busyness factor gamma basically cancels out in the numerator and denominator, and we get something that's deterministic. So within an interval in which we use a single busyness factor, the arrival time should be an IID sample from this distribution F. So that means if we subdivide this interval up into, let's say, intervals of equal length, then it should be that it will always be the case that the number of arrivals in each of these subintervals will follow some multinomial distribution with fixed probabilities. Now you can develop a multinomial test based on this idea. And when you apply this multinomial test, what you'll see within the high intensity data environment, so this is a US bank call center data that Avi Mandelbaum provided to the community a number of years ago. There you have roughly 2 arrivals per second at peak hour. And there you see that this multinomial test actually rejects Poisson structure at timescales of 1 minute and longer. Now in the low intensity environment, so low intensity environment would also be present within the US bank call center data set. If you look at the middle of the night, for example, where you have roughly 1 arrival per minute at off-peak hour. And there the Poisson structure is accepted at much longer timescales. So this multinomial test I've just described seems to be, at least in my view, seems to be a useful diagnostic for looking at Poisson structure. In particular, Poisson structure, even with busyness factors that are present. So we see at the high intensity, in the high intensity environment, that we have a defect in this doubly stochastic model. But now I think the real question to ask is, as I said earlier, every statistical model is going to have the property that it cannot faithfully reproduce every feature in the data. So the more pertinent question is, does this affect our decisions? Maybe before looking at the data itself, let's see what theory says. So we know a lot about call centers. In particular, we know that we have a bunch of very powerful limit theorems that say that when we look at a call center with a very large number of customer representatives, N, with the arrival rate scaling also with N, that the limit theorem says that when you take the number in system divided by N, that converges to some limiting deterministic process little q. When we scale up to get the stochastic fluctuations, we get convergence to some sort of functional of a Gaussian. Now, the thing that's interesting about this result is this suggests that the behavior of this queuing system is going to be well approximated by the limit process Z. And how does the limit process Z depend on the fundamentals of the pre-limit process on the left-hand side? Well, that limit process Z, as I mentioned earlier, is basically a function of the Gaussian process. A Gaussian process is characterized by its covariance structure and its mean. And what is the covariance structure that appears in the limit process? How does it depend on the left-hand side? Well, it depends on the covariances of the arrival process at the time scale of service times. So this limit theory suggests that what you really need to capture in order to understand the behavior of this type of system in the high intensity environment is you really need to capture the covariance structure and the mean of the interarrival process at the time scale of service times. In other words, we don't really care about what happens at the scale of interarrival times. Interarrival times are in the order of seconds. Service times are in the order of minutes. The fine structure of the arrival process down at the time scale of seconds probably is irrelevant. So can we actually ignore fine structure at a scale of minutes or seconds? So let's now turn to that. Which features in the data have very little effect on decisions? What we're now going to talk about is exploratory data analysis, a bunch of tools that we've been developing to study these types of issues. So here's what the exploratory data analysis tool is going to do. We're going to take the empirical sample path data from that US call center, and we're going to run it through the system. Now, what is the system? The system is a queuing model that we've set up that is a reasonable representation of the call center. So we take the empirical arrivals, run it through this queuing system that we believe is a good representation of the call center. So that's the idealized situation where we actually have the empirical, where we have the empirical data itself. Now let's look at trying to build a model from that. Case 2 is we're going to take the empirical sample path data and we're going to split it into intervals of length x. So imagine now that x is 1 minute. Imagine that we look at the kth 1 minute interval. In the trace, 128 arrivals, let's say, arrive in that 1 minute interval. So now in case 2, what we're going to do is we're going to take the 128 arrivals in that interval and we're going to randomly scatter the 128 arrivals as IID uniforms within the 1 minute. So now, what are we doing in case 2? It has exactly the same behavior as the empirical sample path data at the scale of 1 minute. All that we're doing is we're changing the structure of the arrival process on timescales that are smaller than 1 minute by doing this IID random redistribution. In case 3 is another example of the same thing. We again take the 128 arrivals. Now, rather than doing IID scattering, we place them equally spaced throughout the 1 minute interval. And now we run 3 different simulations with them synchronized relative to the empirical trace, and look to see what sort of service times and performance characteristics we get from the 3 simulations. And here's what you see when we do it at the time scale of 3 minutes. So there's the trace data. That is the idealized environment where we're actually using the trace itself. The second case is the uniform redistribution, and the third case is the deterministic redistribution of the interarrivals within the 1 minute. And we can see that, at least to the naked eye, those 3 histograms look pretty much the same. So in other words, the waiting time characteristics that we're getting, that waiting times being a key factor in how we'll make decisions in terms of one design being better than another design. We see that all 3 of these histograms look roughly the same, and when you apply the Kolmogorov-Smirnov test, it will not reject that hypothesis. But when we do things at 6 minutes or at 12 minutes, now we see significant differences. And indeed, now that's suggesting that at the 6 minute level and above, that the sort of replacement that we made does matter. And so the fine structure, the conclusion, at least from my perspective, is that the fine structure at scales smaller than 3 minutes probably does not matter very much in terms of Q performance. But at scales, let's say 6 minutes and higher, it looks like it does. So now we have some sense of what the appropriate timescales are at which we need to begin focusing our statistical attention. So again, the fine scale structure of the interarrival times does not affect performance, at least at scales of 3 minutes or smaller, and we can begin focusing on higher level modeling. Now, how do we begin doing higher level modeling? We begin looking at interval counts based on what happens, let's say, in successive intervals of length 3 minutes. Now, here's another experiment that one can perform, again, of the kind that I mentioned a moment ago, exploratory data analysis tool. How much is the performance at 3 p.m. in this call center influenced by the system state at 2:30 p.m.? So again, now we can run the empirical sample path through the system, and we can compare that with a system that's initialized, let's say, at 2:30 p.m. in its typical state. So what would be the typical state? The typical state would be the typical state associated with just sampling from a random Monday, let's say, at 2:30 p.m. present within the data set. Then between 2:30 p.m. and 3 p.m., we'll synchronize the system so that they're run by identical empirical sample paths. So they'll both see exactly the same arrival process from 2:30 p.m. and onwards. So how much p.m., the closer you get to the trace behavior. The shorter the interval that you use to initialize, the bigger a difference there'll be in waiting time performance. So this is indicating that system performance at 3 p.m. is affected by congestion present in the system. And we can quantify that from this graph. And in order for the system performance to be 10% or smaller, you basically have to go back about 50 minutes. So this is indicating that if you want to look at system performance at 3 p.m., you need to go back roughly to 2:10 p.m. and have a good basic model of the system between 2:10 p.m. and 3 p.m. in order to be able to well replicate system performance at 3 p.m. In other words, you don't need to go back to 9 a.m. You don't need to go back to 12 p.m., but you do need to go back to 50 minutes earlier in order to be able to well replicate system performance at 3 p.m. Let me talk a bit about model building in the high intensity environment. The direction that we've been taking is to try to build a model on a weekly basis. We're trying to estimate non-stationarities across weeks non-parametrically. We are building tools to look at these secular trends. We're looking at parametric modeling of business factors. And again, we can see that in this environment, correlation structure at the level of service times seems to be quite important. And we're looking at models that reflect that correlation structure non-parametrically. In the low intensity environment, it's important to recognize that you can't use the empirical data directly in that context. You need to smooth the data in some way. And that's the setting in which statistically estimating the intensity as opposed to the cumulative intensity function becomes important. In terms of modeling the intensity directly, the standard thing that I think many of us do is to use piecewise constant intensity. Constant intensity Poisson process over successive intervals. But it's quite clear that from an applied standpoint, in many contexts, a piecewise linear intensity would be a better thing to do. Probably we haven't been doing that historically because maybe we view that as being a hard thing to do. The closed form for the maximum likelihood estimator in the piecewise constant case is easily available to us. In the piecewise linear case, there's no closed form, but it is a nice convex optimization problem with linear constraints, relatively easy to work with. One big question that comes up from an applied standpoint in these contexts is how to subdivide the interval. You can see that in the piecewise constant case, for example, we've used a longer interval in the middle where the intensity seems to be roughly constant versus the intervals in which the intensity is ramping up or ramping down rapidly. So how does one subdivide the interval? Turns out there's a dynamic programming algorithm available that computes the optimal subdivision. So the optimal subdivision is optimal in the sense of the corrected likelihood, coming from things like the AIC criterion or BIC criterion that trades off the number of intervals used, the number of parameters used in the model versus the quality of the fit as computed from the likelihood. So there's a principled way of deciding how to subdivide the interval. There are also other alternatives that one can use, kernel density estimators, nearest neighbor density estimators. One thing that one needs to think about in these settings is how are you actually going to use these intensity functions ultimately from a computational standpoint. At least if you're thinking about potentially feeding these things into simulation, whatever intensity model you adopt needs to be something that you can quickly simulate. So you need to think about how to quickly sample from kernel density estimators and nearest neighbor density estimators. Kernel density estimators is easy. That's just a mixture model. We all know how to sample efficiently from mixture models. Nearest neighbor density estimates a much more subtle type of quantity to do fast sampling from, but we do indeed have a good fast sampling algorithm for that as well. All right, so what are some of the takeaways here? For high intensity service systems, we should focus on the structure of the arrival process at the time scale of service times. We shouldn't be worrying about what the structure of the arrival process looks like at the level of inter-arrival times. Don't sweat the small stuff, so to speak. Theory can play an important role in suggesting which features of the data are important. We use that limit theorem to identify the fact that the covariance structure of the arrival process plays an important role. Exploratory data analysis seems to be quite useful. It can identify specific scales at which the theory begins to kick in. And when you think about the statistical models that you're going to use, those statistical models should reflect the computational engine that you're ultimately going to use to study the system. So with that, let me just conclude the talk. Thank you very much.
Let's give Peter a big applause for the excellent talk. And then, are there any questions? And again, you can raise your hand. I think Michel raised his hand. And I think you should be able to speak now, Michel.
Well, in the first place, thanks very much for this wonderful talk, Peter. I had a question regarding your model building slide. So I think it was about, well, basically the period of a week or so. Do I understand correctly? You sample that busyness factor just once every week? And if you do so, are there arguments in favor of resampling it more frequently? Because then you may capture better the effect of that particular day?
Right, so I didn't mean to say that the business factors will be modeled one business factor to the week. We certainly don't want to do that. In fact, it's quite important to do business factor that is intradaily.
Okay.
And the question is, at what granularity should you be doing that? So the main thing that I meant when I say build a model on a weekly basis is, at least within many service operations environments, Mondays, Tuesdays, Wednesdays, Thursdays, etc., actually look quite distinctively different from one another.
Yes, that's exactly what I
want to be
meant.
averaging across the different Mondays that are available.
Yeah.
And
so
not using the same model. Yes.
Please go ahead.
And not using the same model across the entire week, for example.
Yeah, and have you ever thought of using like Coxian processes to model arrival processes. So for some processes with random arrival rates.
Yeah. So I mean, of course, at some level, the busyness factors are one attempt to do that.
Exactly. Yeah.
That's a piecewise constant formulation of the random effect. The challenge, of course, is you not only want to build this correlation structure and this variability structure into the arrival stream, but you also need to include the time of day effects, because that really is first order in a lot of these settings. So somehow, whatever model you build has to respect the time of day non-stationarities that are present.
Yes.
So you want to do both of those things. You want to have an ideal world. You want to have the time of day effects built in. You want to have the autocorrelation structure faithfully replicated at the time scale of service times, at least in many server systems. And you want to have the variability, the additional variability present, so that you get the correct over dispersion. Of course, correct over dispersion, meaning that we've already corrected the data set in the way that I suggested earlier, particularly in settings where you have a very long time series available. There's a good example of more data isn't necessarily better data.
No, I agree. I fully agree with your point of view. Thanks.
Great question.
There's one further question from Weina Wang. Weina, you should be able to speak now.
Oh, hi. So thank you for the insightful talk. This is Weina from CMU. So I have a very high level question. So I was wondering, what made you pick the arrival processes to study for those statistical modeling questions? Like you mentioned that there could be like other aspects of the systems, like the service part. For that, we can also study the statistical modeling questions from data. So I was wondering what made like you choose the arrival processes to study.
Well, you've asked a great question. And it's not because I don't think those are really interesting, important issues. It's just because there's already enough stuff to think about, even on the pure arrival modeling side, to make for some interesting research questions to address. Of course, at some level, if you take the view, which I think is common in many applications, that the randomness in the service times typically comes from the customer and not from the service side, then really the full point process description of the arrival stream is not just the arrival times, but also marks associated with the arrival times corresponding to the service time requirement for each of the different jobs. So that would be the next phase of this research agenda, would be to include that extra layer, that there should be marks, so to speak, corresponding to service times that are attached to each of the arrival times. That would be a more complete description of what one might call the offered load to the system.
Mm-hmm.
And one interesting thing that I think, that I think most of us in the community have historically taken the view that while there may be autocorrelation structure that's present in the inter-arrival times, it's often the case that people take the view that service times are IID. And one interesting thing and I think it's the case that there probably are data sets where the service time distributions could potentially exhibit some autocorrelation structure. Certainly, they definitely would exhibit non-stationarities that are time of day dependent. And if you think about phone calls to a call center, people that call in during their lunch hour probably need to keep their calls relatively short relative to calls that are made, let's say, after work. So my guess is in many applications, the assumption that the service times are IID across the entire day is not a good assumption. They really should be time of day dependent. And there may even be some settings in which you actually see some correlation structure across the service times that is not fully explained from the correlation structure of their corresponding interarrival times.
Mm-hmm.
So lots of interesting issues to think about there. And of course, Moore's talk was extremely interesting in the sense of providing a whole range of new things to think about with regard to service times. So I think that in the operations management context, it's probably more important than in the computer systems setting to also think about some of the modeling issues that relate to arrival times. They probably have as big an effect on performance as getting the service time modeling right. But in the computer systems context, maybe arguably the service time distributions and understanding how to do inference in those things is a much more dominant feature in that context.
I would say even just to add to Peter's comment, even in computer systems, arrival times really matter. So when you're talking about provisioning in data centers, the arrival times fluctuate a lot. And people are always dealing with how to work with these fluctuating arrival times. So so students of mine, like I see Varun is here on, Varun definitely worked on data centers and how to deal with these fluctuating arrival processes and how to deal with power management in that kind of a setting. So we have fluctuations. And it was also interesting, Peter, in your talk, you talked about some of the fluctuations that you expect because they're time of day effects, as opposed to other things that are layered on top that are more variable. Right. I would say even in data centers, when you look, for instance, at Facebook's workload, they show you the time of day effects in terms of the arrival process. There's like a big hump during the day and then a smaller hump for China, and then another big hump the next day and a smaller hump for China. And it goes like that. And they show you these things and they say, but we still don't know about the little fluctuations that happen all the time, which sometimes end up being big, but they are very unpredictable. So yeah, this is all really relevant.
Yeah,
well, that's
I think
cool.
this is already naturally leading into the discussion. So that is wonderful. But maybe before we proceed with that, one final question from Jim Dye. Then we'll take a brief break, and then we'll open the real discussions block of this keynote session. But I'll first unmute Jim. Jim, please go ahead.
Can you hear me, Sam?
Yes, I can. Yep.
Peter, great talk. My question here, I think one point you mentioned the modern arrival process for decision making, right? So that's a very important aspect. So you, and in your example, you use a mini server, some queuing system to test it, right? What's the impact of different models or different arrivals on that? So my question is there any, like in the setting of maybe operation research, operations management, or for maybe data center operations, is there any generic model or simulation model or to test the impact of various arrival models, right? Is this such thing? I mean, should some of us making that effort to build that, or that something has to be problem specific, right? If you work in call center, you build a simulator for call centers or something. So that's really my my question along this.
Jim, I think it's a great question that you've asked, and I do think that having a simulation tool that is roughly representative of the decision environment in which you want to use the simulation to make decisions is a very, very good thing to do. So the idea that I was describing with exploratory data analysis is that the exploratory data analysis is sort of a first phase of the statistical analysis where you're trying to understand what features of data seem to be important to making the decisions. At that level, I think you're correct that you could have a somewhat stylized model that you use to try to understand, roughly speaking, what features need to be well represented within the statistical model that you're building. Of course, once you actually get to making the decision itself, at that point, you'll have built the statistical model, potentially based on some of the insights from the exploratory data analysis. And then, probably invariably, at that phase, the simulation model might be much more granular in terms of representing a lot more fine structure of the system that you want to think about from a decision-making standpoint. But I think this first phase, the exploratory data analysis phase, is something where you don't really want to be using necessarily a highly granular simulation model. Something that is relatively simplified already is probably giving you a lot of insights into what features need to be faithfully replicated in the statistical model that you built. So I think having different simulation models of that kind that could be used in concert with this exploratory data analysis tool would indeed be a quite useful thing.
Thank you. So basically maybe in our community, maybe research shouldn't be focused on that high fidelity simulation model. That's a job of Uber or something like Google. Internally, they should build that, right? We maybe should focus on the front end of maybe better off more front of than, right? The building the model and testing at like you said, exploratory analysis, maybe at the high level, that may be more, you may have more impact in that segment of the research.
Yeah, I think that's correct, Jim. I would agree with that.
All right, thanks.
Okay, I see that